In the last session, we've seen the zero sequence networks for the transformer in a different configuration. In this session, we'll see the sequence impedances and networks for a transmission line and the importance of positive and negative sequence networks. Just once again, the recapping the switching diagram, which is useful for deciding the connection between P and Q for the transformer in the zero sequence mode. That is, and the switching diagram you are making use to determine path from P to Q for a different configuration. That is, we are seeing switch A and C is meant for primary side, B and D is meant for the secondary side. Then the series switch, that is A and B, they are the operating when it is a star connected, and C and D, it is operating when the delta connection. Okay. For example, if it is star connected grounded in the primary, in that case, the switch A should be closed. Star, that is the primary star connected and grounded, A should be closed. If it is only star connection in the primary, then A is open. Of course, there is no operating C because it is the star connection, the operator A should be operated. C is kept open. Now, instead of the star connection, if you have got the delta connection in the primary, in that case A should be open and C should be closed. C should be closed. That is the primary. Similarly, the conditions are holds good for the secondary also. That is, if the star connected grounded, switch B should be closed. If it is star ungrounded, B should be open. If it is a delta connection in the secondary, in that case, the delta switch D should be closed. This is how we have to make the total connections from P to Q, that to represent the zero sequence network for the transformer. Then sequence networks of a transmission line. We know that the positive and negative sequence impedances of linear symmetrical static circuit, that is the transmission line, are identical because the impedance of such circuit, that is a transmission line, is independent of phase order provided the applied voltage are balanced. The impedance of a transmission line to zero sequence current differ from the impedance to positive and negative sequence current that we are discussing in this session. That is, it is the positive and negative sequence impedance of the transmission lines, they are equal. They are equal. That is, the conductors of the transmission line being passive and stationary and do not have an inherent direction as such. Therefore, the transmission line or a cable may be represented by a single reactance in the single line diagram. That is, if we are representing a transmission line in the single line diagram just by showing a line there, and thus they always have the same positive sequence impedance and negative sequence impedance, meaning that as in the case of the transformer, in the case of the transmission line also, the positive sequence impedance or reactance is same as its negative sequence impedance or a reactance. Means positive and negative sequence impedance are equal in the case of the transmission line also. However, the zero sequence path also involve a returning path, that is earth path or earth wire, and the earth return path. That is why the zero sequence impedance is higher in the value, because here in the zero sequence current path there is a return path is involving. That is why the zero sequence impedance or a reactance is greater than the positive and negative sequence reactance or impedance of a transmission line. The zero, positive and zero sequence impedance of transmission lines are represented as series impedance. As such, it is I told you, it is a passive. It is being a passive element and a stationary element. As such, there is no source involved here. Therefore, in the positive, negative and zero sequence diagram, it is represented by respective impedance or a reactance. The same thing is displayed here, that is zero sequence network as represented by zero sequence impedance, and the terminal voltage is VA0 and the current which is flowing in the zero sequence network is IA0. Similarly, in the positive sequence network is represented by positive sequence impedance or a reactance, and the current which is flowing in the positive sequence is IA1 and the terminal voltage is VA1. Then in the negative sequence network, that is, it is represented by a Z2 and the current which is flowing is IA2 and the terminal voltage is VA2. This is how we have to represent the transmission line in zero, positive and negative sequence diagram. Then we'll move to the sequence networks that will concentrate on the first, the positive and negative sequence diagram. The objective of obtaining the values of the sequence impedance of a power system is to enable us to construct the sequence networks for complete system. That is why we are determining the sequence impedance of the different elements in the power system, so that you have to draw a complete the positive sequence, negative sequence and zero sequence network of a whole power system. The network of a particular sequence show all the paths for the flow of current of that sequence in the system. That is, if you are drawing a positive sequence network of all the components, then you are getting a path of that particular the sequence network. For example, if you are representing positive sequence network, it is consisting of all the positive sequence representation of generator, transformer, transmission line, motor, everything, then the current in that particular path is a positive sequence current. Similarly, negative and zero sequence. Therefore, the matching reactance in a positive sequence network is the subtangent, transient or synchronous reactance, depending upon the whether the subtangent, transient or steady state conditions are being studied. That is, in the positive sequence, if you are representing for the synchronous generator, it is depending upon which current you want to determine. Whether you are interested in the subtangent current, that is soon after immediately after the fault, so that the current is very high. In that case, your positive sequence reactance should be XD double dash or subtangent reactance. Then you have to take subtangent reactance as its positive sequence reactance. If you are interested in determining a transient current and the positive sequence reactance should be your XD dash or it is a transient reactance. If you are interested in the steady state current of the fault, in that case the positive sequence, the reactance is nothing but its synchronous reactance. This is how we have to represent the positive sequence network of the synchronous machine. The reference bus for positive and negative sequence networks is the neutral of the generator. That is, neutral of the generator is the reference point. So far as the positive and negative sequence components are concerned, the neutral of the generator is at ground potential. That is, the neutral of the generator is ground potential, even if this ZL is connection between the neutral and the ground. That is, in the while drawing the positive and negative sequence diagram, our reference should be ground. It is at a ground potential. The reference bus for the zero sequence network is ground, not necessarily the neutral of the generator. That is, it is very important statement that the reference bus of the zero sequence network is ground. It is not the neutral of the generator. That is, neutral is, it is the floating in this case because it is an unbalanced condition. The continuing that is to draw these sequence networks from positive to negative, convert positive sequence network to a negative sequence network by changing, if necessary, only the impedance that represents the rotating machine and omitting the EMF. That is, we know that in the case of the positive sequence network, we have got a representing with the source and its positive sequence reactance. However, in the case of negative sequence diagram, you have to omit the source and it is represented by its negative sequence reactance. The normal one-line impedance diagram plus the induced EMF is the positive sequence network. That is, I told you, it is source of voltage and its positive sequence reactance. Three-phase network and motors have internal voltage of positive sequence only. That is, we have to represent the positive sequence network with a source for generator and motor only. Okay, with this background, that will solve some numericals on the positive, negative and zero sequence network, how to draw the network using the equivalent, that's sequence networks of different components in the power system components.